Hi, welcome to Introductory Statistics. In this session, we're not going to get into too much technical detail about statistics. We're just going to cover some basic things so that you have a base of knowledge going forward for the rest of the year. So we're going to talk more about concepts, talk about the vocabulary, talk about the things you need to know in order to start your first statistics class in a couple of weeks. So we're really teaching thinking in terms of statistics here tonight, not necessarily technical details, although we will get into them to an extent. So when we're thinking about statistics, what we're really interested in is the relationship between two variables. This should be familiar from the other classes that you've taken this week. And what we're saying here basically is that y is some function of x. In statistics, basically what we're trying to do is figure out what that is. Does y equal x? Does y equal x squared? Does y equal 2x? And so forth. For the most part, when we're trying to assess this, in statistics we'll have data about x and y, but we don't necessarily know what the nature of that relationship is. And what statistics helps us do is learn about, first of all, whether this exists, because it could very well be that y is not a function of x. And that's what we want to use statistics to learn. So when we think about the relationships between two variables, think, for example, of height and weight. We probably would assume that height and weight have some sort of relationship. What is the nature of that relationship? And that's the sort of thing that statistics can help us learn. In social science, we try to make sense of the world by understanding these relationships. And in public policy, this is particularly important because we may have the ability to tweak y, and if we can tweak y, then we may be able to affect x. And that's really what we do in public policy, is try to adjust the things that we can in order to achieve some desired outcome. And we need to know the nature of the relationships between those inputs and those outputs if we want to have effective public policy. So we use statistics sometimes to figure out what the nature of these relationships is, what the nature of these relationships are, and sometimes we have a specific idea about what those relationships are going to look like, and we use statistics to decide whether or not the real world actually works that way. We can also use statistics if we are just probing for relationships. There may be variables that we don't expect to have relationships, but they are there, and those might be important. So today, we're not really going to get into too many technical details. It's mostly going to be an overview of concepts and things like that. You're going to have plenty of time over the next 2 quarters to learn about the technical details. But we're going to talk conceptually so that you can hopefully understand the language of statistics and not be quite so intimidated whenever you sit down and start learning these technical details and looking at Greek symbols and all those sorts of things. We're going to do that by looking at 6 key issues that you need to understand as you think about statistics. We'll talk a little bit about sampling. We'll talk about measurement. We'll talk about probability, distributions, relationships between variables, and finally, inference. So the first thing to understand about statistics is the importance of sampling. What is a sample and why do we sample? A sample basically is any subset of a population about which we're interested in learning something. So we could call everyone in this room a population. And if I wanted to learn something about this population, I could take a sample of 5 of you, and I could learn something about the broader population by just talking to the 5 of you. Now, you may ask, why wouldn't I just talk to everybody? This is a small class, it's a small population. And that's true. In a small population, I probably could talk to each one of you and have not just a general idea about the characteristics of the group, but an idea about the total characteristics of the group. But in reality, that's usually not practical. We usually can't survey an entire population unless we have the resources of the United States federal government, in which case we can to varying degrees of success and ability, but by and large, we have to sample. We can't take a census. We can't gauge the entire population. We can only gauge a sample of that population. There's a couple of things that are important to understand when we talk about sampling in populations. Within a population, that doesn't necessarily just refer to the population of the United States. Sometimes it does, but we can have other populations. Our population of interest might be graduate students. It might be students at Ohio State. It might be neighborhoods in Columbus. It might be the states. So our population is not just people. The unit of analysis is the smallest point at which we want to get information about some set of characteristics. So if we're interested in the effects of some state-level policy, we may look at the state to look at how outcomes have been achieved in a state. If we're interested in community level, we might look at census tracts. If we're interested in individual characteristics, then we're going to look at people. But our unit of analysis can be virtually anything. In social science, it's usually something to do with humans or human organization. But every field has different units of analysis. By and large, in public policy, you're going to be looking at individuals or some way of grouping individuals, be that organizations, neighborhoods, census tracts, those sorts of things. So the population consists of the full allotment of those units of analysis. A sample is any subset from that population. So if I wanted to say that the group in here was a sample, you could be a sample of students at the Glenn School, students at Ohio State, graduate students in the United States, people currently in the United States, or the entire world population. You're a sample of all of those. You're not a good sample of any of those, which I'll talk about in a moment, but you are a sample of all of those. Why aren't you a good sample of that? Well, because you're not random. Whether we're talking about Glenn School students, Ohio State students, or the world population, you are not a random sample of people from that population. You are here because you want to learn about statistics, or maybe you don't want to learn about statistics, but you've recognized that you have to learn about statistics. So you're here voluntarily, so that makes you a biased sample. You aren't representative of the population. You're part of the population, but you're not representative of it. You haven't been selected at random from the population to take part in whatever survey I happen to be interested in doing with you. So the important characteristics of a sample are that they be random and unbiased. By random, what I mean is that whenever you're establishing the sample, you want that sample to be constructed such that every single individual in the population has an equal chance of participating in the sample. So how pollsters do that is by calling phone numbers at random. They pick random phone numbers, they call, and thereby can say that, for the most part, almost everybody has an equal chance of being a participant in the sample. Now, you're also a biased sample, because you're not here to take part in the survey, you're here to learn about statistics. So you're a biased survey. If, for instance, I was to ask you questions about your proficiency on the math portion of the GRE, well, you're a biased sample of that, because you've probably recently taken the GRE, so you're pretty familiar with it. So I'm not going to get a good read on how the general population would do on it by asking you, because you're a biased population. So those are the basics of sampling. We sample because it's impractical to cover the entire population, and because we want to know something about that population. As I'll get to when I talk about inference, we use a sample to infer things about the population. And in public policy analysis and public administration, we want to know how policies and how the actions of public agencies are going to affect people. So sampling is very important. It's how, in policy analysis, we make sense of the policies that we've enacted. In order to understand how those policies work, we have to measure them in some way. So that gets to the second thing I'm going to cover today, measurement. within our sample, we have individuals. Whatever the unit of analysis is, we have individuals, and those are our observations. So each one of you would be an observation in a sample if I were to say you were an unbiased random sample of Glenn School students. Each one of you would be an observation. Each one of you has variables associated with you. Say, for instance, your GRE score, your years of education, your age, your height. All those things are variables about you that are different for each one of you. All of those variables were measured in some way. And that's what we do with a measurement. A measurement is simply the property of a person or thing about which we want to make some sort of a comparison, so we need to quantify it in some way. So we have to measure it in some way. Now this can range and be pretty basic. So if I wanted to measure your GRE scores, well, you probably know what you've gotten on your GRE. So we can do a direct comparison of those. I could have each one of you come up here, and I could measure your height, and we could figure out what the average height of everyone in the room is. Those are pretty self-explanatory measurements. But we can also measure other things. When I say that we're quantifying things, it doesn't have to be a complicated quantification. We could say that, for instance, if we wanted to compare males and females, we could just say males are 0, females are 1. We've quantified it, it's measured. It can get complicated though, of course, when we're talking about things like that. For instance, say one of the things we want to assess is someone's political ideology. How do we measure whether someone is a conservative, a liberal, a moderate? It gets a little bit more difficult. What about honesty? How do we measure honesty? How do we assess the extent to which someone is honest? So within measurement, one of the things that all measurements have in common is error. Every measurement has some sort of error in it. And that even includes relatively simple things like height. If I had a measuring tape and all of you came up here and I measured your height, well, there's going to be some measurement error. To some extent, I'm going to round. So I'm not going to have anyone's exact height. I'm going to round your heights to the nearest ½ inch or something like that. And so there's going to be some random error in there where I'm estimating some below, some above, and extrapolate that all together, and there's error in that measurement. Some of it might also be that I'm just completely incompetent to measure your heights, and so the person doing the measuring is doing it wrong. That's another measurement error. When we're talking about a political ideology and we're trying to measure the extent to which someone is conservative, well then we can have a whole host of measurement errors. What we may be testing may be completely invalid. Now it's probably true today to say if you're a Republican, you're a conservative, so that might be one way to measure it. But in the past, that wasn't necessarily true. As recently as 50 years ago, if you were a Northeastern Republican, you probably were pretty liberal. So there are a variety of different measurement errors that we have to be aware of. What we want in a measurement is a lack of bias. That is, we don't want to be systematically overestimating or underestimating what we're interested in measuring. Some of our measurements are going to be higher, some of them are going to be lower, and our measurement is unbiased to the extent that we're not systematically doing it one way or the other. We understand that there's going to be error, and we're okay with that, because there's always going to be measurement error, but we don't want to be systematic about that, about where that bias lies. We also want our measurements to be reliable. We want them to be reasonably precise. So if each one of you came up here and I measured your height, I should get roughly the same thing every time I measure you. If I measure you 10 times, I should get roughly the same thing each of those 10 times. If I'm getting wildly divergent measurements, then I'm doing something wrong. So whenever we consider measurements, it's really important to know what we're trying to measure and how we're measuring it is valid, unbiased, and reasonably precise. And this is important because moving on to the third thing that I'm going to cover tonight, probability, we want to be able to assess the probabilities of a set of circumstances given a set of measurements on variables. Probability is important because we are interested in randomness. There are lots of random events take place. And a phenomenon is a random event to the extent that it's not predictable. Its outcome is not predictable, but yet over the long term, there are some predictable trends. And the probability of any outcome of these random phenomena is the proportion of times that that outcome will occur over a long series of repetitions. So let's think of this again in terms of if I were to measure your heights. It's going to be a random variable, your specific height. That's a random occurrence. I can't predict exactly how tall you are, especially with you sitting in a chair. Those are random. I could say that you're 5'8", but I don't know that. But over time, if I were to have a constant stream of people coming in here, over time, I would start seeing some trends. I would be able to predict some probability of people's height. They would converge. So even though one specific event is random, over the long term, there's a probability about what the nature of that variable is. And the simplest way to think about this is flipping a coin. When I flip a coin, it's whether it's heads or tails is a completely random event. I don't know in advance if it's going to be heads or tails. If I did, I wouldn't be going to grad school. I would be somewhere in Vegas making a lot of money. But every time I flip a coin, I don't know if it's going to be heads or tails. I know it's going to be one or the other, but I don't know which one of those it's going to be. There's a 100% chance that it's going to be one of the two, but I don't know which one. However, if over time I sat up here and flipped a coin, and I just kept flipping a coin and recording the results, what do you think would happen? Over time, if I keep flipping a coin, say I flip it 100 times, say I flip it 1,000 times, 10,000 times, 100,000 times, the more times I flip it, the closer the probability is going to be that I'm going to see I have a 50% chance of flipping heads. If I do it twice, I might get 2 tails. That's not going to really tell me a lot. Those are still random events. If I flip it 100,000 times, each one of those 100,000 flips is a random event, but I know that over time, I'm going to have flipped about 50,000 heads and 50,000 tails. So that's what we're talking about with probability. So probability, we'll just go quickly through a couple of the rules. A probability is any number between 0 and 1. And if we're interested in whether or not what event is going to occur, well, we know the probability is between 0 and 1. Either something's going to occur or nothing's going to occur. So, the probability that I'm going to let you leave class early tonight is pretty low. The probability that you're going to be bored is pretty high. But those aren't fixed rules. We don't know where that probability lies. We just know that it's somewhere between 0 and 1. If we add up all the possibilities, they will tabulate to 1, because we know that something is going to happen. We don't know exactly what's going to happen, but something is going to happen. So even though there's a very low chance that I'm going to let you go early, it's still possible. There's a much greater chance that I'm not going to let you go early. And if we add up the chance that I let you go early to the chance that I don't let you go early, it's going to equal 1. I'm either going to let you go early or I'm not. One of those two things is going to happen. A few moments ago, I used the term independent when I said these flipping coins are random and independent. What I mean by independent is that knowing the outcome of one event has absolutely no bearing on the outcome of another. So you might think, and the classic example of this is someone in sports. You might think that, let's say I'm a baseball fan. So I might think that Ryan Howard is really on a tear lately. He's hitting lots of home runs. He's on a streak. He's on a hot streak. Well, sort of, but not really. Over time, those things are going to even out. He's going to hit about 275, 280. He might be hitting 350 in the last 2 weeks, but he's going to end up hitting 275. What he does in one at-bat is completely independent of what he does in the next at-bat. They're two independent events. And though we may think that he's hot, athletes don't get hot or cold. Over the long term, they perform to some level at which their skills, abilities, and a knowledge allow them to compete at, and that's what they do. The sequence of events is completely independent. Think of, in basketball, the player having a hot hand. Well, they really don't. They may have hit 5 shots in a row, but they may well turn around and miss the next 5 in a row. The events are independent of one another. The law of large numbers, though, is what tells us that over time, some trend is going to occur. Like I said, Ryan Howard's going to hit 275. Well, over time, he's probably going to do that. He may be having a good week, he may be having a bad week. And despite the fact that Phillies fans live and die with every single at-bat, it's a silly way to look at things because in the end, he's going to do approximately what we expect he's going to do. So why is the law of large numbers important? Well, because it allows us to make inferences about how variables in the population work. And one way to understand this is through the use of looking at distributions. So the fourth thing I'm going to talk about today is distributions. The distribution of a variable simply tells us about how many times a certain variable has a certain value. So let's say, looking in this room, if we did the height example again, there would be some set of heights that we would have. Some of them would be more likely to occur than others. So, something around 5'8", 5'9", 5'10", that would probably occur much more frequently than, say, 7'2". We might have someone that's 7'2", but that would be unlikely. So what will happen is we'll probably see something like this occur, where let's say this is 5'9". 5'9" will probably be about the most common height. We'll have about half the group below there and about half the group above there. Most of you are going to be somewhere in here. Our 7'2" person would be out here somewhere, and that's not entirely unexpected. It's just that there's not going to be very many people that have that. The size underneath this curve is indicative to how many observations we see at that point. So the 7'2", that would be an outlier. It's an unexpected value. It would be unique. But if someone is, say, 5'10", that's not very unique. This 5'9" is the point at which this curve is highest. So that means the point at which it's highest is the most likely value. What do you think the most likely value, if I were to measure all of you, and if I wanted to guess any one of your heights, what do you think I would guess? I would guess 5'9". Why? Because that's the most likely value for that variable, and it's going to be the mean. So when we're looking at a normal distribution, and this is a normal distribution, if I put a mirror in the middle here, it's going to look about the same on either side. That's a normal distribution. The normal distribution is very important, and you're going to learn a lot about it this year. So I'm just going to give you some really basic stuff right now. The normal distribution reaches its highest point at the mean. So the most likely value for the variable, if I look at a sample, if I look at a population, the most likely value of that is the mean. So what is the mean? You all know what the mean is. You know what the average is, but what does that actually mean? Let's say, we talked a little bit earlier about denoting variables in some of the previous sessions. Let's say that height is a variable x. How would I determine the average height of everyone in this room? Well, I would measure everyone's height. Let's say I is an individual, x is their height. I measure everyone's height, and I add them together. Oh no, it's a Greek symbol. All that means is that I sum everyone's height together. So I sum all of your heights together, and I divide by however many of you there are. So don't let this Greek symbol scare you. It just means you add everything together. This is the equation for the mean. The sum of all observations of the variable divided by the number of observations we have. And if this holds true, that would equal roughly 5 feet 9 inches if I gauged everyone's height. In a normal distribution, the mean is going to be exactly the same as the median. The median is the number at which half of the values are below it and half of the values are above it. I've given you the formula for that in your formula sheet. But basically, the way you calculate it in a normal distribution is quite easy. It's going to equal the mean. But if you have a skewed distribution, say something that looks like this, where a large proportion of the observations are towards the lower end, but there's a few more stacked in the upper end of the tail. We would say that this is a skewed distribution to the right. So if we have this skewed distribution, think of income. Most people aren't rich, but there are quite a few rich people. So most people have an income that's down here towards the lower end of this range, but there are, a number of people who are up here at the upper end. Well, the median then in this case is going to be at the high point. Half of the values are going to be below this, half of the values above this. But the mean, because of the preponderance of values at the upper end of the scale, the mean would probably be somewhere out here. So that's one of the reasons why the Census Bureau reports median family income. Because this is really a more important number if we're looking at income than this. Because this is being dragged up by the Bill Gates and Warren Buffetts of the world. We're not really concerned about the extent to which their income affects the income of the average American. That's why we use the median for that. The mode is the other measure of central tendency, and that is the most common observation. In a normal distribution, it should be somewhere around the mean. It doesn't necessarily have to hold that way for most distributions, though, but it will probably be somewhere close to the mean or median. The other thing a distribution tells us is something about how spread out the variables, or how spread out the observations are. Spread is important because it tells us about the precision of whatever we're measuring. How much clustering is there? So if we think of this in terms of a distribution, if we see a distribution that looks like this versus one that looks like this, obviously the observations are more clustered here and they're more spread out here. The mean in this case tells us a lot more than the mean in this case, because there's a lot of observations far away from the mean here, and most of them are quite close here. So that variability is important because it tells us about how spread out the variables are. It tells us about how much confidence we have that this mean actually tells us something. And this is very important for inference. We want to know what the mean of the population is. We use the sample mean to give us an idea about what that population parameter is. And we know by looking at the variability how likely it is that this sample mean is close to the population mean. Now, to think conceptually about what spread or variability means, let's go back to our normal distribution. So we know that the mean is right there in the middle. What does the spread tell us? With the normal distribution, we have a really good rule of thumb that helps us know something about how the spread or the variability affects our ability to assess the population. And this is the 68, 95, 99.7 rule. What that means and this is why standard deviation is such an important thing to know. If we have a normal distribution, if we've taken, say we've done some sort of a survey, and we've asked approval ratings for President Obama. Let's say our mean is 50%. Well, if we have a normal distribution, we know that approximately 68% of the people that we ask are going to be within one standard deviation of the mean. We know that 95% of the people we ask are going to be within 2 standard deviations of the mean. And we know that virtually everyone is going to be within 3 standard deviations of the mean. So what does that mean? Well, if we have a small standard deviation, then we can gauge this mean pretty precisely. Let's say that we have a normal distribution and our standard deviation is 1%. That's a very small standard deviation. Well, what we would know is that 68% of the people we polled have an approval rating somewhere between, rated Obama's performance somewhere between 49 and 51%. That's pretty precise. We would know that 95% are somewhere between 48 and 52%, and virtually everyone is somewhere between 47 and 53%. Now, if we have a much bigger standard deviation, say it's 10%. Now we have substantially less information, because this tells us that 68% of people rate his performance somewhere between 40 and 60. 95% rate it somewhere between 30 and 70. And virtually everyone rates it somewhere between 20 and 80. What does that really tell us? Are you surprised to hear that everyone in the population rates his performance, for the most part, somewhere between 20 and 80? That tells you very little about what we're actually interested in looking at. That's why spread and variability are important. There are a couple ways that we assess spread. The standard deviation is important when we're concerned about the mean. When we have a normal distribution, we want to know the standard deviation so that we can know things like this. If we have a very skewed distribution and the median, if we're thinking of something like income, and the median is the better measure of central tendency, then we may want to use something different. We may want to look at the minimum and maximum values. We may want to look at the 25th and 75th quartiles. And the calculations for those are available in your notes. I'm not going to go into those right now. Distributions, though, are important because they allow us to understand what we're really interested in when we're talking about statistics. We use distributions, we use the characteristics of distributions to assess relationships. And that's the 5th thing I'm going to talk about today, relationships. Relationships get back to this. What we're really interested in is knowing the relationship between X and Y. So let's say Y is your GRE score, and X is your years of education. We think there's probably some relationship. Your years of education probably has some effect on your GRE score. So we use statistics to learn about the nature of that relationship. We want to know if these two are indeed associated with one another. How do we think they might be associated with one another? In all likelihood, there's a positive association. So So in your graphing class the other day, you did some basic graphing where you looked at plots of x and y. Let's say that this is GRE. This is your years of education. So one of you might be here. One of you might be here. Somebody might be here. Somebody might be here. Here, 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 here. So you're going to be all over the place there. But we're probably going to see some trend that looks something like this. That is, as your years of education increases, your GRE score increases as well. That's a positive association. We expect these two variables to be positively associated. We don't necessarily know the nature of that relationship, but we expect y equaling f of x to have some sort of a positive relationship, whether it's y equals x or y equals 2x, whatever the case may be. We do not expect y equals negative 2x. If we expected that, then we would see something like this. Where as this variable increases, this one decreases. That's a negative association. In statistics, we would officially look at this, and we would call these correlations. We would want to know the nature of this relationship. We would want to know if these two variables are correlated. How much are they related to one another? How much do they vary together? And is there some sort of a systematic relationship in that varying? Now, you've probably heard the term that correlation is not causation. And that is absolutely true. By plotting it like this, even if we found a really strong correlation, we can't say anything about causation. We can't say that more years of education causes higher GRE scores. We may want to infer that, but we can't say that definitively. And a great example of this is I remember a couple of years ago, there was a commercial on TV saying something along the lines of, kids who ate Frosted Mini-Wheats did better in school. So what they were saying is that eating Mini-Wheats and grades have this sort of relationship. And they were strongly implying that it was causal, that the more Mini-Wheats you eat, the higher your grades are going to be. That's not causal. It can be a variety of different things. It's probably the case that kids who eat any breakfast get better grades. It's probably the case that kids who eat breakfast have more attentive parents, and they therefore get better grades. It's probably the case that kids who have access to breakfast every day are wealthier and therefore get better grades. That is, there's a variety of lurking and confounding variables that don't allow us to say that one thing causes the other. We can say that they're correlated, and we may want to investigate that relationship, and we may want to make speculative statements about causality, but we do not ever prove causality. So when you're taking your statistics classes this year, do not ever say that one thing causes something else, or at least Professor Desai will surely let you know that you're wrong about that.